Okay, welcome back everybody for the second part of our video lecture on section 2.4, measures of variation. So last time we computed the standard deviations for this data set that we've been working on for a while, and we want to see if we just round to integers. The mean turned out to be around 25, and the population standard deviation was close to 14. We wanted to find how many of these values are within one standard deviation of the mean. Okay, so that would be, so 25 minus 14, I believe, is 11, and 25 plus 14 is 39, right? Okay, so we'd like to see how many values, number of values that are between 11 and 39, and we'll include the endpoints, right? All right, so here's 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15, and that's it, right? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so it looks like they're about 15. Okay, if I haven't missed any. So that's 15 out of 28. Okay, which is what was it? Just a little bit over 50%, right? 15 divided by 28 is about 54%. Okay. All right. So about a little more than half the values are within one standard deviation of the mean. And I think we can all agree that all the values are within two standard deviations of the mean, right? Because 25 minus 28 is negative 3, and 25 plus 28 is should be 53, right? And all these values are in those. So we're talking about 100%. Within two standard deviations. Okay, and so we want to think like, well, what in general, what percentage of the data can we expect to be within 1 or 2 or 3 standard deviations of the mean? And there are two ways to answer this question, depending on the distribution of our data set. First answer is the empirical rule, which says that if we know ahead of time that it's a symmetric distribution with a symmetric bell-shaped distribution. So we talked about what we meant by symmetric from frequency diagrams. That means that it was symmetric, and the tall bars were in the middle, and the very short bars were at the end. And a bell-shaped, I think, would mean that we're talking about something like this, if we were to sort of draw a curve through the tops of all the bars of a histogram. Then, if we know that ahead, we can expect that 68% of the data is within one standard deviation of the mean, 95% is within 2 standard deviations, and 99.7% is within 3 standard deviations of the mean. Now, last time we said that in our example, it turns out that this was really 54% and this was 100%. But we're talking when the populations get very, very large, or the size of the data sets gets very large, we can expect this. Obviously, we're not going to get exactly that. But this is the picture I want you to get in your mind for the rest of this course. This is a bell-shaped distribution. We're going to see that this first part indicates that the bell is always centered at the mean, and the 2 inflection points occur at 1 standard deviation from the mean. So this middle section represents 68% of the values. And then here we have mu minus 2 sigma and mu plus 2 sigma. So this region and this region and this region correspond to all the values that are within 2 standard deviations of the mean. So this, from here to here, we're talking about 95%. Okay, and when you do that, you take 95 minus 68, divide by 2. That's how you get the 13.5 and the 13.5 here. And then if 90% of the values are in here, then 5% will be outside of this value, outside of this white region. So this is divide by 2, you get 2.5 here and 2.5% here. And actually, of course, then like mu plus 3 sigma would be okay over here, and again something over here. But we're really just saying if it's going to turn out that if something is more than 2 standard deviations of the mean, we're going to call that unusual. So that we say a data entry is unusual if it is more than 2 standard deviations from the mean. Okay. So to keep that in mind here. So, all right. So that's the empirical rule. It's also called the 68, 95, 99.7 rule. Okay. We say that now another way we can talk about distributions, which is Chebyshev's theorem. And the main thing here is we need to know about the what the distribution looks like. It doesn't have to be symmetric or bell-shaped. It says for any data set, the proportion of data within k standard deviations from the mean is given by this number 1 minus k squared. Now, this doesn't really, I should say that k has to be greater than or equal to 2, because obviously if k equals 1, then this is just 0. So I'll say that, let's assume k is greater than or equal to 2. So if k equals 2, we have 1 minus 1 over 2 squared, which is 1 minus 1/4, which is 3/4, which gives us 75%. Okay. So if it was bell-shaped, we said that there would be 95% would be within 2 standard deviations. But even if we don't have that, it would get at least, we can expect at least 75% to be in there. And then if we have 1 minus if k is 3, we get 1 minus 1 over 3 squared. That's 1 minus 1/9, and so that is going to be 8/9, which I think is around 89%. Okay, so that's how much you can expect within 3 standard deviations. So we can see that we don't have, once we get past 3 or 4 standard deviations, there's hardly any data that's outside of that region. Okay, so that's Chebyshev's theorem, and the good news is we are not going to prove this. If you want to see the proofs, I'd say you can take an upper level statistics course. All right, but let's see how we could just use this in a few examples. So in this example, if we have a mean of 2,500 and the standard deviation is 150, we know that 2,500 2,500 minus 150 is, let me just check my arithmetic here, is 2,350, and 2,500 plus 150 is 2,650. Okay, so we see that between 68% would be between 2,350 and 2,650. 95% we would have 2,500 plus 2 times 150, so that's 2,500 plus 300, so this would be 2,800, and I'm sorry, this would be 2,200. That's 2500 minus 300, and then 2500 plus 300 would be 2850. And then between three standard deviations, 2500 minus 450 is 2050, and then 2500 plus 450 would be 2950, right? Great. Okay. So let's see with this next question. If a sample of 50 of size 50 is taken, how many values can we expect between 25 and 2800? Well, let's look at our picture now. Again, here's our bell-shaped distribution. It's centered at 2500, and here's 2800. Okay, we're talking about 2 standard deviations from the mean, right? From the center of the mean to here. So, well, what was that? Well, we know that this little tidbit over here was 2.5%. Okay, and we can see that this is, from here onward is 50%. You can see 50%. So we're really talking about this region right here. This region plus this region is 50%. So 50 minus 2.5 is 47.5%. Okay. And okay, well, if 50, the sample is 50. By the way, this 50 and this 50 are not related to each other. This 50, we're talking about the 50% that are to the right of this mean. And then so what we would have is our sample size of 50. We have 50 items. What would be 47.5% of that? We just take 50 times 0.475, right? Okay, and then this would be approximately 24. So you'd expect a little less than, almost half. Okay, which is, kind of makes sense. All right. Okay. If you wanted to find, let's say let's say if we wanted to find between 2500 and 2650, okay, this would be about 34%, right? Because we basically be cutting this middle region in half, right? So from here to here would be 34%. So it would be 50 times 34% would be approximately whatever it is, because I didn't do this ahead of time, and I suck at arithmetic. But actually, it's exactly 17, so that's how many we could expect there. There's just a couple things you should be able to recognize, from a picture which has the smaller variance and which has the larger variance. In this case, it should be clear that since the data is really scrunched up up here, and where it's a little more evenly distributed here, so we can see that sigma 2, in fact, should be greater than sigma 1. Okay, I guess it really doesn't care about what the relation between the means are. Okay, we can just see from there. Another example. Well, suppose we're given some information about these two companies and the company's salaries. Company A has a mean salary of 80,000, and Company B has a mean salary of 78,000. But as we said before, the means don't always tell us the whole story. In one, we have a standard, in the Company A, we have a standard deviation of 3,500, and in second, we have a standard deviation of 6,000, right? Okay, so so you say, who cares? Well, if we look at Company A, and draw a picture of what's happening here, and let's assume that these are both bell-shaped populations, bell-shaped symmetric distributions. Okay, so here's 80,000. Okay. Okay, if we go one standard deviation over, that is 83 500. Right? We just added this to this, and that's one standard deviation away. And we can see that this 13. This, as we said, this is 13.5% of the salaries are in this range. For Part B, here is 78,000, and one standard deviation takes us all the way. We add these two numbers together, we get 8,400, right? Okay, which is interesting because, or 84,000. So this is actually bigger than this, even though this has a bigger mean. And what that says is that you can do some arithmetic. You can, so we know that you can do the arithmetic, and see, it'll turn out that both this region and this region is 36.5%. Now, how do we get this? Well, we know it's 50% from here to here, and then add another. So this region would be, we take 100% minus 50 minus 13.5, and that's how we get 36.5. And so do the same thing here. This is 13.5%, and this would be 36.5%. Okay. Well, what it means here is that there are how many, we have more people in company B who are making over $83,500, because over here 83.5 would be, or 83,500 would be over here. So in company A, we have 36.5% people are making more than 83.5 thousand. In Part B, we're not sure how much more, but we have quite more than 36.5% are making more than 83.5 grand. So, like I said, the mean only tells us part of the story. The variance is also the variance, and in particular the standard deviation is also important. So, I've given you a lot to think about here, and I will see you next time.